Welcome to this recording of Chemactivity 1, Essential Ideas. This activity is really designed to cover some of the background material that shows up in Chapter 1 of our text. In this course, I assume that you've been exposed to these ideas before the course has started. What I recognize is in reality that will be true for some of you, but not for others. And so this activity is really designed to help you review it or encounter it for the first time as needed. As you read the text, and I encourage you to do so, here's some basic ideas that I suggest that you use as you're reading. The first part of the chapter, sections 1.1 to 1.3, are pretty descriptive. In other words, there's information there that I think you should be able to digest just by reading. The second part, sections 1.4 and 1.5, are more quantitative. There's going to be calculations and manipulations you need to do, and so this activity is really going to focus on those two sections. In particular, we're going to focus on reporting and manipulating significant figures in a calculation and converting between units. If when you're done with this activity you still have questions, and that would be a very normal thing to have happen, please come in and see me or get some help from someone else in the Chemistry Instructional Center in Education 107. Let's get started. The first part focuses on significant figures. What is a significant figure and why do we need to know about it? First, let me give you the definition. The significant figures in a reported number are those that one knows for sure plus one that contains some uncertainty. So for example, if I report that I weigh 125 pounds, I am certain that it's a 1 in the hundreds place and a 2 in the tens place. So I know I don't weigh 250 pounds, for example. I know it's 120 something. The 5 is uncertain, and that's because my scale isn't super precise. So it might be 126, it might be 124. So I know the 1 and the 2 and the 5 is uncertain. All three of the digits are what we call significant figures or significant digits. Now, why do we need to keep track of them? Whenever a chemist or other scientist takes a measurement, we are using some sort of instrument. In the case of this example, we're using a scale or a balance that might be in my bathroom. And we need to keep track of how precise that measurement is. And we do that by keeping track of the significant figures. So when we report numbers, we have to be able to count significant figures. And in lab, you will do that based on the measurements that you actually take. In class, I'm going to give you numbers and you need to be able to count and figure out how many significant figures are in a value. So here are the rules here. And I'm not going to read them because you can do that right now, but we're going to practice applying them. So I'll refer to them as we go through these examples. So if we look at the first example, 1.003, notice that rule number 1 is all non-zero digits are significant. So that means the 1 and the 3 are definitely significant figures. If we look at rule 2, zeros that are between non-zero digits are significant. So that means that the zeros, because they're between the 1 and the 3, those are significant digits or significant figures. So that means we've got a total of 4 significant digits in that first value. If we look at the next example, we can see we've got zeros, but now they're not between two significant digits, so what do we do with them? Zeros to the left of the first non-zero digit are not significant. So these zeros are to the left of the 4. And so that means in this case only the 4 and the 5 are significant. So that means we've just got 2 sig figs, which is our shorthand for significant figures in that second example. If we look at the next example, zeros that fall at the end of the number and to the right of the decimal are significant. So remember that these first 3 zeros, just like in the case up here, because they're to the left, they don't count as significant figures. The 4 and the 5 count because all non-zero digits are significant. And now we've got another 0. It is to the right. It falls at the end of the number and to the right of the decimal place, so it is going to be significant. So the 4, 5, and the 0 over here will be significant, and that gives us 3 sig figs for that example. If we look at the next example, we've got something now in scientific notation. And we need to look at this rule here. only digits in the coefficient of a number written in scientific notation count toward the sig figs. So this part here is the coefficient. This is the exponent. So we don't need to look at the exponent in order to count the sig figs. It matters because it tells us how big the number is, but the sig figs are only going to be determined by the coefficient. So we look at the 2 and the 3, and we say all non-zero digits are significant, and so we end up with 2 sig figs there. If we look at the next one, again, we have to only look at the coefficient. We've got a 2.03. The 0 is between two non-zero digits, so that's going to give us 3 sig figs. The 2, the 0, and the 3 are all significant. If we look at the next example, 2.030, so the 0 that's in between is definitely significant, and the 0 here that's at the end, but to the right of the decimal place, is also significant. So that gives us 4 sig figs in that example. The next one is a little bit different. We've got the number 2000, and we can see that the number ends in zeros, so they're at the end of the number, but we don't have a decimal place here. And so this is ambiguous. We don't actually know whether the zeros are significant or not in this case. And so in general, I will tell you, I won't give you examples that are like this one, but I just wanted to point it out that it is ambiguous there. In the last number, 2000.0, now we've got a 0 that is to the right of the decimal place, and that's going to make all of these that are in between it, all of the other zeros, significant. So this is going to be 5 sig figs in this last example. One thing to recognize is when you do calculations with your calculator will give you lots and lots of digits, and they may or may not be significant. You're going to have to be able to keep track of them when you are manipulating numbers. And so what we're going to do next is learn how to handle significant figures when we're adding, subtracting, multiplying, and dividing. So how do we handle significant figures when we're adding and subtracting? So the rule is here. The result of addition and subtraction has uncertainty in the same digit as the number with the largest uncertainty that's being added or subtracted. So for example, if we look at these two numbers being added together, we can see that the uncertainty, remember that's the last significant digit, in this case it's the 2 for the 4.02, that's in the hundredths place. In the first number, it's actually in the thousandths place. And so this is a larger amount of uncertainty because it's in the hundredths place. So that means that when we add them together, our uncertainty, the value that has the uncertainty, has to be in the hundredths place. So if we add these two together, we get 16.023. And I am just going to underline the 3 to indicate that it's not that that number is uncertain. I have no idea about that number. And that's because I had no idea what the value here would be, because there was just no digit there. So that means I know the 16, I know the 0 in the tenths place, and the 2 in the hundredths place is uncertain. So I will have 4 sig figs in my answer, and when I report it, I would report 16.02, and I would not report the 3 because I don't have any idea about the 3. We can do a similar process for this next example. So notice that in this example, we're subtracting one number from another, and the uncertainty in the first number is in the ones place. Here the uncertainty is in the hundredths place. So when I subtract the 24.31, the value that I end up with has to have uncertainty in the ones place. So let's see what that looks like. When I plug it into my calculator, this is what I get, 15306.69. But remember, because I really don't know anything about the tenths and the hundredths, because I didn't know anything for the 15331, that means I really can't report those as significant. The number that has some uncertainty in it is the 6, because I knew both the 1 and the 4 here. So that means when I go to report it, I'm going to report 15307, Notice that I'm going to round up here because the 0.6 is going to force me to round up that 6 to a 7. Let's look at the last example. This one is a little bit different because it's got exponents. In order to know what digit to follow, we need to convert all of these to the same exponent so we can look just at the coefficients. Remember, it's the coefficients that determine the significance of the digits. So I'm going to convert all of them so that they have a 10 to the 4th coefficient. Notice that when I do that, I've got uncertainty in the tenths place, and then way out here in the thousandths place. So my result is going to have uncertainty in the tenths place. So if I plug these numbers into my calculator, what I get is 27.701 times 10 to the 4th. And remember that my uncertainty needs to be in the tenths place. So that means I am going to underline the 0 and the 1 as being insignificant. So the first thing I can do is rewrite this as 27.7 times 10 to the 4th. Now, in general, when we report values in scientific notation, we need to report them with a coefficient that is not as large as this. So we need to convert that to something between 1 and 9.9. So what we would do is now convert this to 2.77 times 10 to the 5th, because we're going to move the decimal place over by 1 to the left, and that's going to increase our exponent by 1. So that would be what we would find our final reported value would be. So that's addition and subtraction. Now let's look at multiplication and division. The rules for multiplication and division are actually much simpler, so most students prefer them. And the rule is that the result of a multiplication or a division process has the same number of sig figs as the number with the least number of sig figs being multiplied or divided. And the reason this works, and you don't need to know all the details about this, is this maintains approximately the same percent error through the problem. So if your uncertainty was about 2%, then your result will still have about 2% uncertainty. So let's look at some examples. Here I've got two numbers that are going to be multiplied together, and I've already written the result down here. This number has 5 significant digits, and this has 8 significant digits. Remember, we're going to go with the least number of sig figs, so that means our result can only have 5 sig figs. So I'm going to underline all the numbers that are not significant. We always start from the left, 1, 2, 3, 4, 5, so that means all of those are going to be insignificant. In order to report this, I'm going to convert it to scientific notation. So I'm going to say 5.3484 times 10 to the 5th. And that's because I had to move my decimal place over 1, 2, 3, 4, 5 in order to convert it into scientific notation. And the reason I really needed to do that is because I wouldn't be able to report nothing in the ones place. So I just needed to be able to get rid of the ones place entirely. So remember what we did is the result has the same number of sig figs as the number with the least. So this was the least. So our final number only has 5 because this only had 5. Let's look at another example. We've got two numbers being multiplied here. This one has 3 sig figs and this one has 2. And that means our result can only have 2. So if I underline things that are not significant and then think about how I would report that, I would report 0.015, because I'm going to need to round, times 10 to the minus 5. And that's not a great way to report something in scientific notation. So I'm going to move the decimal place over 1, 2 in towards the right. And so I'm going to end up with 1.5 times 10 to the minus 7. So go from 10 to the minus 5 to 10 to the minus 7. The same rules would apply if we were dividing. So even though there are no examples there, the rules would be the same. A couple of things. You've already seen me demonstrate some rounding rules. So when we report a final result, we have to report it with the correct number of sig figs, and the value to the rightmost significant figure to be reported is based on the insignificant digit immediately to the right. So if that digit was more than 5, we round up. If it's less than 5, we leave it as it is. The other thing, and we'll see this in the next section, is that numbers that are exact do not limit the uncertainty in a calculation. So numbers that are defined to have a certain value have no uncertainty, and so then they don't impact our calculations. So for example, 1 foot is equal to 12 inches by definition. So the 1 and the 12 are exact. They don't have any uncertainty in them. And so we wouldn't count these as significant digits. Same thing, a kilogram is 1,000 grams. All numbers are exact. For a value something like this, 3.02 grams per milliliter, this was something that was based on a measurement, and so this would have significant digits. It would not be exact. Let's look at a few examples where we have both addition and subtraction and multiplication division. This is going to follow the same rules you would have learned in a math class. We're going to do any operations in parentheses first, then we're going to do multiplication and division, then we'll do addition and subtraction. And we have to keep track of all the digits, even the ones that are insignificant, until the final result is reported. So let's look at the first example. So we've got a number in parentheses, but that's not actually an operation, that's just an exponent. So the first thing we're going to do is this multiplication step. So that's the value I get, and because I'm using the rules for multiplication and division, my values here had 5 sig figs or 3 sig figs, so my result here can only have 3 sig figs. So I'm going to underline all of those numbers as insignificant. Now what I need to do is add the 2.44 and subtract the 42. And remember, now we need to keep track of which digit we're looking at. I find it helpful to line these up so I can see the digits, so I'm going to do that now. Now, when I look to see where my uncertainty is, remember these are all insignificant, so I don't know them at all. So it's the 9 that's out here in the hundreds place that has the largest uncertainty. It's the digit with the largest uncertainty. So that means when I add all this together, I've got to really focus on the hundreds place. Okay, and so what I can see is that I don't have any idea. I mean, my calculator tells me values for the tens, the ones, the tenths, hundreds, and thousands, but I don't really know these because I didn't know them here. So that means I can only report these 3 significant digits, and I'm going to have to report it as in scientific notation. So I'm going to report 1.29 times 10 to the 4th. Let's look at the next one. Here we're going to need to do this division problem and this division problem before we can do the addition of subtraction. So these are the numbers that I get when I plug it into my calculator. Notice that here I've got 3 sig figs and 3 sig figs. So my result here can have 3 sig figs. The zeros out in front are not significant, as we learned when we were counting earlier. So it's going to be the 3, 6, and the 0 that are significant. And that means the last 3 6 are not significant. Here I've got 3 sig figs divided by 2 sig figs. So that means my result can only have 2 sig figs. Remember that the zeros out in front are not significant, so my first 2 sig figs are the 3 and the 9, and then the rest of them will be insignificant. So now, because I'm doing addition and subtraction next, I'm going to line it up so I can see the digits. So remember, in addition and subtraction, we look at what digits do we know. Here we know the tenths, hundredths, thousandths. Here we know all the way out to the 10,000ths. Here we know out to the thousandths. So notice I'm just going to draw this kind of in green here to say that's going to be our cutoff for the digits that are going to be significant, because we know them in all 3 of the numbers being added and subtracted together. So this is the result I get, and remember that because I can only know the first 3 decimal places, that means the 7 and the 5 at the end are going to be insignificant, And so what I would report is 0.258, because I'm going to round up because of this 7 here. I'm going to hold off on this question here until after we have done conversions, which will come in the next section. So you'll see examples that are like this. On to part 2. It's frequently the case that we are going to have a sample that might be described in one unit, and we're going to need to convert it to a different unit. So for example, let's suppose you had a pile of stuff, doesn't matter what it is, maybe it's iron or salt or something on the counter. And we happen to know that what its mass is in pounds, and we want to know instead what is it in kilograms. So the sample itself isn't changing. We're just going to describe it in terms of kilograms instead of in terms of pounds. In order to be able to do that, we need to know what the relationship is between pounds and kilograms, and we do that using conversion factors. The first thing we need to do to create a conversion factor is to know the relationship. So it happens to be that 2.20 pounds is equal to 1 kilogram. Since these two things are equal to one another, in other words, they describe the same quantity, just in different units, we can divide one by the other, for example. And what we get on this side is everything cancels out, and this side becomes 1. So that means that 2.2 pounds over 1 kilogram is like a 1. And anytime that we have something that's like a 1, we can multiply something else by that 1 without changing its value. So since these two things, meaning the 2.2 pounds and the 1 kilogram, are equal to one another, then we can, and in this particular case I divided through by 1 kilogram, but I could have divided through the other direction, so I could get either of these relationships. And because we're allowed to multiply a number by 1 without changing its value, we can use this kind of relationship to change the units. So for example, if I weigh 115 pounds, what is my weight in kilograms? To do this kind of calculation, we always start with an actual quantity that we're interested in. So in this case, we're interested in my weight, 115 pounds. We start with that. And then we multiply it by a conversion factor, which remember is like multiplying it by 1. In this case, we want the conversion factor to allow me to cancel out the pounds and be left with kilograms. And in that case, I want pounds to be in the denominator so that the pounds will cancel here. So I'm going to use this version. 1 kilogram over 2.2 pounds. Remember, this is just like multiplying by 1, which I'm always allowed to do. And what I get is 52.27 kilograms. And I need to pay attention to my significant digits. Here I was multiplying and dividing. So I've got 3 sig figs, 3 sig figs, 3 sig figs. So my answer can have 3 sig figs. And so I end up with 52.3 kilograms. Let's make sure we know what we just did. Remember that I haven't changed my weight. My weight is whatever it is. All I've done is I've said, well, my weight, if I measured it on a scale in pounds, might be 115, and all I did was convert it to a different unit. So my weight is still the same real quantity, but I can either describe it in pounds or describe it in kilograms. So here's some general rules to use. Start with a quantity that you know, in this case the 115 pounds. It's a real thing. Write it with its units, because you want to be able to see, for example, in this case, that the pounds cancel and you're left with kilograms. Find a conversion factor, in this case we used this one, that is derived from an equality. And the equality is this, it's two things that are equal to one another. Orient the conversion factor appropriately with respect to the units. In other words, I chose this one so the pounds would be in the denominator. multiply and make sure your units cancel out in the process. Let's do a couple of examples. I am given an equality. So here's an equality. And remember that I can take that equality and I can convert it into a conversion factor. So I can either say 14.6 psi over 1 atmosphere, or 1 atmosphere over 14.6 psi. Either one of those things is like a 1, and I can use it to convert from one unit to the next. I'm going to start with the value that I've been given. So let's read the whole problem. Given this equality between psi, pounds per square inch, and atmospheres, if my bike tires need to be pumped up to 90 psi, how many atmospheres of pressure will this be? So I'm going to start with what I'm given, 90 psi, pounds per square inch. Now I'm going to choose a conversion factor, either this one or this one, that will allow me to cancel the psi. Since I have psi in the numerator here, I'm going to want the version that has it in the denominator here. So I'm going to choose this one. And so I can see that my psi are going to cancel here, and I'm going to be left with atmospheres, which is what I want. Now I just take the numbers and put them in my calculator. And what I get is 6.16438 atmospheres. Now I need to check my sig figs. So I had 3 sig figs here, 3 sig figs here, 3 sig figs here, so my result can have 3. And so I'm going to report 6.16 atmospheres. So what that tells me is that if I have a pump that reads 90 psi, that would be the same value in pressure as 6.16 atmospheres. Look at the next one. In a 2-liter bottle of soda, how many milliliters are there? Now this allows me to go back to an idea that we presented earlier, and that is that 1,000 milliliters being a liter is an exact relationship. So this is not going to impact our significant digits. But we're going to do the same kind of process. We're going to start with what we're given, 2 liters, and we're going to make a conversion factor. And let me just note that I know that I'm going to have liters on the bottom and milliliters on the top, because I can see that I want my liters to cancel. So I can arrange the units even before I put the numbers in. And now I can go to my equality and see, okay, my equality tells me that there are 1,000 milliliters in 1 liter. So I can put the numbers in after the fact if that helps me to make sense of things. So then what I'm going to get is that I'm going to get 2,000 milliliters. Now remember that this relationship here doesn't limit my significant figures, so this is going to limit my significant figures, 2 sig figs. So that means those 2 zeros are not significant, but this one is. And so the best way to report this is using scientific notation, 2.0 times 10 to the third milliliters. So in a 2-liter bottle of soda, there are 2.0 times 10 to the third milliliters. In the previous example, we just had a starting value and 1 conversion factor. But sometimes we have to use multiple conversion factors to complete a problem. So we've been given a set of equalities here that we could use to create conversion factors. And we've got an example that we're going to use multiple conversion factors here. So the example is, if you run the 100-yard dash, how many kilometers have you run? Now, if we had a conversion factor that went directly from yards to kilometers, then we could do that in one step. But in this particular case, that's not what we've been given. And so we've got to start with our 100 yards, just like we have before. And I've created space for a conversion factor. Since we have yards, we're going to need to do something to get rid of the yards and go to some other unit. So I'm going to use that 1 yard equals 3 feet. So I'm going to put 1 yard. I don't know why I made this space so small, but I did. 3 feet. So that's going to allow me to get rid of the yards and go to feet. So now I'm going to need some way to get from feet to something else. So let's go from feet to inches. So we'll go 1 foot is equal to 12 inches. So that's going to allow me to cancel out the feet, and I'm left with inches. So now I'll go inches to centimeters. So that means 1 inch is equal to 2.54 centimeters. And notice I can cancel out the inches here. Now I'm going pretty quickly. Notice the pattern of what I'm doing. In each case, I started with something that had a unit, and then I'm looking for a conversion factor that has that unit in the denominator so I can cancel it out. So I got rid of the yards, got rid of the feet, got rid of the inches. So now I'm left with centimeters. Now I haven't put any numbers in my calculator yet, but I know that this is the unit that I would be left with if I put all those numbers in my calculator. Now I'm not after centimeters, so let's keep going. I want to get to kilometers, but let me go from centimeters to meters. So I'll use this one here. So I'm going to go 1 centimeter equals 0.01 meter. And that's going to allow me to cancel out the centimeters. And then I'm going to use my last one here. 1 kilometer equals 1,000 meters. And so I get 1 kilometer is equal to 1,000 meters. And so I can cancel out my meters. Now, notice that I've got the only units that I have left are kilometers, which is good because that's what I want. Remember, I started with my 100-yard dash. I want to know how much is it in kilometers. I've paid attention to my units all the way through. So now all I have to do is say, okay, put in my calculator, 100 times 3 times 12 times 2.54 times 0.01 divided by 1,000. What do I get? So I get 0.09144 kilometers. Now, the sig figs here are a little messy, and I shouldn't have done this way, but remember that these zeros here are ambiguous. We don't know what they are. So I'm going to assume that the only significant digit I have here is the 1. So that means that everything but the 9 is going to be insignificant. So I would report 0.09 kilometers. Now, notice that one of the things that I did was I made sure that as I went along that my units were canceling. And what I find is that students understand that part of the process. And sometimes what students make mistakes with is they put units in, but then they don't have numbers that actually belong in the conversion factor. So one of the things you have to make sure of is anytime you have a relationship like this or a relationship like this, that this thing is true. In other words, these two things are really equal to one another in a relationship like this. And if you can find a place where these two things are equal to one another, then you are allowed to put them in a conversion factor together. Okay, our last topic is about the metric system units and how we convert between them. So I've got a table here that lists a factor and a prefix and a symbol. The symbol goes with that prefix. And what is sometimes confusing is how do we write the relationship? So let's say, for example, we're going to use milli. And let's say we're going to talk about grams because we're wanting to measure mass. In this case, our base unit is the gram, right? So the grams are not on this table. Our base units are things like grams or liters or meters. The factor goes in front of the base unit. So we would say 10 to the minus 3 grams is equal to 1 milligram. So just in terms of reading this table, 10 to the minus 3 goes in front of the base unit, and then the prefix or the symbol for the prefix goes in front of the base unit on the other side. So 10 to the minus 3 grams is equal to 1 milligram. Now we can rearrange that, if we want to, by dividing both sides by 10 to the minus 3. And what we get when we do that is, of course, on this side, that turns into 1. And on the other side, 1 divided by 10 to the minus 3 is 10 to the positive 3. So we could rewrite this as 1 gram equals 10 to the positive 3 milligrams. But if you're reading off a table that's like this, the factor will go in front of the base unit. Now you can rearrange it if you don't like the negative exponents, but the factor as written will go in front of the base unit. Let's go to the next page and use this a little bit. So we have an example of a conversion factor here. Let's make sure we know where we got it. So remember that we said that 10 to the minus 3 liters is equal to 1 milliliter. And that's a minus right there. Now if we rearrange this and divide both sides by 10 to the minus 3, then what we get is 1 liter equals 10 to the 3rd milliliters. And if we rearrange that into a fraction, we get one of these, we get either of these. So that's where that came from. Let's see how we use it. Something like this. A high-energy physicist measures the time between collisions of atoms in a fluid. The time is 30 femtoseconds. So you have to know that F is femto. If you didn't know that, you can just Google it. What is the time in seconds? Well, the first thing we need to do is figure out what femto is. And if you look it up, because it's not on the table on the previous page, you have to Google it. What you find is that femto, 1 femtosecond, is equal to 10 to the minus 15 seconds. So if you were to find that in a table, femto is the prefix, 10 to the minus 15 is the factor. And remember that the factor always goes in front of the base unit, which in this case is a second. So we now have an equality. Because we have an equality, we can use it as a conversion factor. So now we're going to start with what we've done before, which is start with what we're given, 30 femtoseconds. And we're going to arrange our conversion factor so that the femtoseconds is in the denominator and the seconds is in the numerator. That's going to allow our femtoseconds to cancel. Now let's put the numbers in the right spot. 10 to the minus 15 goes with the seconds, and 1 goes with the femtoseconds. And so what we end up with is 3 times 10 to the minus 14 seconds. And I just assumed here that this 0 was not significant because it's ambiguous, so I just kept the 3 over here. Okay, so that finishes our essential ideas. Again, if there's things that are confusing about this, come in and absolutely get help. There's nothing wrong with that.